encoding-decoding architecture, right? So it was the last thing we talked about. So we started with the sequence-to-sequence models. We talked about how we can build a language model, right? Do you remember that? What was the idea last time we did? We got a recurrent neural network, right? Something like an LSTM. So this was the idea. Yeah, that's okay. So we wanted to make the neural network to start talking, right? And talking coherently in a language. So we said we're going to collect a bunch of sentences, right? And then we're going to mark them with the start and end. And we're going to mark them with start and end. And the next thing was that we're going to tokenize that. So we're going to have a chart. Then every token is specified by a number. You can represent that number either by a one-hot vector, the simplest way, or you could do embedding. At the end of the day, you're going to have a sequence. And that sequence is the thing you want your neural network to learn to generate, right? And the way that we do it, we start to just pass every single sentence through that neural network. Every time we make the neural network to select the next token as coming from whatever it has seen before, right? So the start goes in without anything. And then we're going to get the first sentence at the output. Then we're going to have the next token going in. We have the memory as well. That memory is going to contain whatever we have seen up to that point in the sentence. That one is coming into the neural network again, and it's going to generate the next token. I don't know what is wrong with this. I mean, 2026, we're still dealing with this issue. It's really annoying. So, yeah, next token comes out, the next token come in, and then the memory goes in, the next token comes after, and so on and so forth, right? So if we give it enough sentences, it starts to understand how it can put the right token after the other, right? And that is going to resolve the key issue that we had, right? Or that is going to build the language model that we wanted. Now, we talked about this, that if we want to make this neural network to now talk about a particular image, in the image captioning case, for instance. What can we do? We could essentially put the image, and then we try to extract a feature out of it, right? We get the image, we process it, maybe we do use a convolutional neural network, and then that convolutional neural network is going to capture a bunch of features. Those features go in as the initial state, right? And then your neural network starts to just generate a sentence that is a coherent sentence, and hopefully it's going to be about this image, right? So that was the idea, how you can build one image captioning model. This is one example of what we call it encoder-decoder architecture. So encoder-decoder architecture in general is consisting of two bodies. One of them is the encoder. The encoder is going to get your input, and your input could be an arbitrary sequence, right? Here, if it is an image, this is basically a sequence of length 1. It could be one complete sentence, right? Maybe you want to do translation, right? So you're going to get your input, you're going to give it into a neural network. That neural network is responsible to look at that data and extract a bunch of features, right? Those features are hopefully the required concept or context inside the input that you require to generate your output, right? So this is why we call it encoding, because it's getting the data from its own data space, image, right? It's going to extract or encode it into a bunch of numbers. Those numbers are meaningless to us, but it's meaningful for the neural network, right? And the neural network can use them as a kind of feature in order to generate the output. Everybody's cool? Question? Okay. If you think like that, then you're going to have a decoder which is going to generate the output for you, right? It's going to look at the features that had been generated by the encoder, right? And going to get that one. The decoder could be of any form. Here, as you can see, because we are thinking about the image captioning case, I'm keeping it to be an RNN, right? Because I want to generate a sequence, right? But if you don't want to generate a sequence, for instance, you can put another architecture here, right? And then this guy is going to get the features and it's going to process it into the output that you want, right? And now, again, here it starts from the feature space. The feature space is the features that, again, are meaningful to your neural network, but they are pretty much meaningless to you, right? And it tries to generate a kind of data which is now meaningful to you, right? So it's getting from feature space back to the data space, but it could easily now change the space of the data, right? You could start from image, you land in the text, right? And so on. Everybody's cool? Okay. Now, you might tell me what kind of neural network you could use in practice. Well, any neural network could be encoder, any neural network could be decoder, right? If you want to think very strictly, what you have done up to this point had been a very simple example of encoding-decoding. When you wanted to classify an image, what do? You give it into a bunch of convolutional layers, right? Those convolutional layers extract feature for you, right? And then you give those features into the MLP to classify finally, right? That MLP is essentially a kind of decoder, right? So it's going to look at those features and it's going to generate the label that you want, right? And this convolutional part was essentially an encoder, right? But it was so simple that we did not call it encoder-decoder, right? But here you can use any encoding and decoding. That totally depends on the data type that you have, right? For instance, if I want to get a sentence and generate an image related to that sentence, what should I do? What would be my encoder? What is your choice for encoder? You want to process a sequence, right? The sentence. What do you use as encoder to process it? You can use an RNN, right? This RNN is going to start from the first token, process it to the second token, third token, towards the last token, right? If you look at the state of the RNN in that last token, that is going to summarize everything inside the sentence for you, right? Because it has seen the whole sentence, correct? Then you're going to get that state and pass it into some decoder. What would you use as a decoder if you want to generate an image? You can use a CNN, right? You can use a CNN, which is starting from a small map of initial state and somehow generate for you one 3-channel 100 by 100 image, right? So you can do this. It's possible, right? Theoretically, it's possible. If you implement that, it's not going to be a very, sophisticated architecture, or it doesn't work that fine because it's too simple. But theoretically, it's possible, right? So you can encode using a sequence model, decode using a CNN, right? So you can use anything here, and anything there is always encoding-decoding. You typically call it encoder-decoder when you are really processing, at least in one side, you are processing a sequence. Okay? Yeah. Start is the start token, like start the sentence.
But there are no other inputs.
No, yeah. You can say, for instance, randomly take a token, right? For example, I mean, typically what you do, you get here start, and then you get the first word, right? The first token. You're going to give the first token in the second time as the input, right? You can do that. You could sample, but still you give the probability vector as the input. You can do all other sort of things, but they are usually just implementational tricks. Okay, so if we think about this particular example that we have here, we could have used CNN here, encode, and then get the features to generate the sequence at the output. I can replace it with whatever I want, right? I can use ResNet here. I could use simple MLP here, and whatever I use here is going to extract me at the end of the day a bunch of features, right? And those features are okay, right? The only issue is that if the model is too simple, then the features are not rich enough to capture all the context inside your data, right? Make sense? Now, that is the way that you model this, or you build this model, but the question here is that how you can do the okay, let me see. Yeah, how you can train this architecture. Do you have any idea how should I train this guy? I should train it end to end, right? So I'm going to briefly elaborate how you can train it, but the key point here is that, I mean, these features that are generated here, if you just train your encoder separately, right, it's going to generate a bunch of features which might not match the decoder, right? In order to make the decoder to understand the language of the encoder, you need to train it all together, right? Which means that the first image goes in, you get the first caption, right? You compare it, you compare your output to the ground truth caption that you have in your data set, compute the loss, you take the gradient, right? You backpropagate, you find the gradient with respect to all the ways inside the decoder and encoder, you update, right? You keep doing this. At some point, they start to understand each other, right? So it's going to generate features which are understandable for the decoder, right? So the training is going to be end-to-end. Now, one thing that I want to briefly mention here, and I'm not going too deep into that here, but like if you have the other courses like generative AI, we're going to get more deep into that. That is the idea that you can look at the neural network as a kind of conditional distribution. And if you think like that, then all these modeling and encoding, decoding makes sense to you. So what is the idea here? Is that when you are having a neural network, essentially what you do, if you think in terms of supervised learning problem, you typically are training a conditional distribution, right? And whatever you do for training, when you, for example, minimize the loss, you essentially minimize or maximize the likelihood of that statistical model, right? So to just give you the idea here, let's think about the classification problem. So if you have a classification problem, you're going to get the input, maybe your image, to your neural network, right? That image goes into your neural network. There are a bunch of computations happening. At the output, you're going to get a Y, right? What is that Y typically when you want to do classification? It's not label itself. What do we compute typically? Softmax, right? Softmax is going to give you a distribution over all possible labels, right? Everybody's cool? Yeah? So if you think in that term, then that softmax output is essentially giving you the probability of every class given that you have seen this data, right? So you can think about the whole process as a conditional distribution. Make sense? So what I could say if I have k different classes, then the output Y is going to be one softmax output, right? And this softmax output is a probability distribution. Now what is Y1? Y1 is the probability of class 1 happening given that I have seen data X, right? It means that what is the chance of data X being label 1, right? If it's very small, then it means that, okay, it's not possible, right? It's very unrealistic to think like that. So you typically take the guy which is having the largest value, and essentially you are just taking the guy with the maximum likelihood, right? You would say which guy is the one which is most likely to be, which class is the most likely class, the one which has the highest probability, right? So every single output that you have, you could say it's the probability of my label being the particular label that I'm looking for, given that I have seen my input data, right? And if you think in that sense, then RNN essentially at every single time is giving you the probability of the next token, next output, right? Given whatever it has seen up to that point. Make sense? If you think about the output at time t, right? And let's think in terms of the language model. So at time t, language model is giving you one output. What is that output? It's again a softmax, right? This softmax is giving you the probability of every single token happening, right? So it's going to say token I is happening with this probability, right? Token M is happening with this probability, and so on, right? Depending on how many tokens you have in your dictionary, right? So this YT at the output is a probability distribution, and if you think about one single guy in it, YKT, this is the probability of token K being your next token, given whatever goes inside the neural network, right? What do you have inside your neural network? You obviously have your XT. This is the token at time t, right? This is the token, the word that you have right now in the sentence, right? This is one thing. The other thing is HT minus 1, right? The state of your neural network up to that time, right? And that state, what is it encoding into it? It's encoding the memory about the whole sequence, right? So if you think about this HT minus 1 to somehow carry the HT minus 1 to carry the information about x1 to t minus 1, which was the whole purpose when we started building this RNN, right? We wanted to build one model which has a memory, and that memory is capturing everything before, right? So if you think of this HT minus 1 to capture information about this guy, you essentially say that, okay, this HT minus 1 is whatever information is about, or relevant information, useful information I have from time 1 to time t minus 1, right? And then I look at time t, right? So essentially I'm looking at the whole sequence 1 to time t, right? Whatever happened from beginning of sentence up to this point, and now I want to talk about the probability of the next token, right? And it makes sense. Even we talk like this, right? If I keep talking, if I want to just build a sentence, initially when I say nothing, you have no clue what I want to say, right? If I say I, then you probably start to build some intuition, right? The next cannot be potato, right? It should be am, have, something like. If I say am, then you probably narrow down your prediction, right? You would say the next one is most likely an adjective, right? Happy, then you probably say, okay, it's going to finish because it doesn't make sense to have anything after that, right? So you start to care, and the longer I speak, the better you can predict what I say, right? So this is exactly what happens inside the neural network, right? So every single time it's capturing whatever context you had up to this point, right? And then at that point, it's going to predict what is the next token, right? Everybody's cool? Questions? You got the idea? Now, yes?
So this is like the idea of Bayesian inference.
Sorry?
Like the Bayesian inference.
I didn't get the term.
Also Bayes.
The Bayes influence?
Yeah.
Yeah, somehow, yes. If I give you, I mean, you typically when you talk about the bias in training, you mean like a general overall bias. And because here it's not a bias simply, yeah, I mean, given the sentence you are getting a bias, but the key point is that you actually have no other option, right? Typically when we talk about the bias is that you want to train this language model, you only show it good sentences, right? Optimist sentences, right? So it's never going to talk sad, right? Then this is bias toward happiness, right? This is typically when we mean by, what we mean by bias. So everybody got the idea here, how you can think about this neural network, the language model? Now, if you think like this, you are thinking statistical. And you might tell me what is the difference to what we have done up to this point. Well, here I do not really pay attention to the fact that this HT minus 1, the state that I'm capturing from my neural network, how efficient that guy is, right? Well, you know from previous chapter that you could have a very simple RNN, and probably the gradient is going to vanish, and then this means that this HT minus 1 is not really capturing whatever is inside sentence, right? So that is what happens computationally, right? Or design is limited by the computational limits that we have on or in practice. So this HT minus 1 is not really representing x1 to t minus 1, right? But when I think of statistical, I forget about these practical things, right? So I just think that, okay, let's say there is a way to do that, right? What is the way? There is no exact way, but I can approximately do it by this or that approach, right? Now, if I get this and I want to generate the next token, I should sample from a conditional distribution, right? This is the way that people think statistically. And of course, you need all the way, both approaches to build a neural net or AI system, say, or AI model. But when it comes to implementation, you typically get stuck into the computational steps, right? Whereas when you want to design a new thing or understand an overall architecture, you probably need to have a bit of a statistical understanding, okay? Cool. So what I can say, for instance, here in this data set, in this architecture, I could say I have this, this input and this image, and then my encoder is going to extract some feature, right? Now again, I assume statistically that these features are going to capture every information inside the image, right? Well, you do know if you want to make it very efficient, you might have a hard time, right? You need to play with different convolutional layers, maybe you need a skip connection, other things to make it really work, right? But at the end of the day, let's say that it works, right? Then you're going to have a bunch of features. Now you give the features, you give the first token to your RNN, it's going to say, oh, this is cat, cute, and so on. I need to start the sentence, right? What is the most probable thing to sample, right? It should be something about cat, right? Such is a kind of valid start point because I can say such a cute cat, right? But I don't know. Ali is not a valid token, right? Because there is nothing about Ali inside this image, right? So it's going to sample such, right? Now it's going to get such. Such comes as the next input. And then such is the token now, right? Information that I have from before is containing everything that I need. A cat, it's cute, it's an image I want to talk about, right? Everything. And both of them go inside, then what is the chance of the next word, right? The next token. Well, is going to be one of the valid choices, right? So you're going to sample that one, such right? And then it goes for cute, same thing. Now, when you get here, well, you have such a cute. This is what you had inside your sentence, and it's about a cat, right? So what would be the next token? Well, it could be cat, it could be kitty, but it could not be dog, right? So dog is not going to happen. That token is not going to happen with high probability. The ones which have high probability are either kitty or cat, right? They are very high in probability, right? And depending on the calculation that you do and the sampling that you do, one of them comes out, right? And this is why when you talk with a language model nowadays, you're going to get different responses. They are conceptually the same, but if you prompt same thing from the same language model, it's going to give you different things, right? Because there are lots of random seeds involved in between, which makes the computation different, which makes the sampling different, right? But it never goes to talk about something totally irrelevant because they are not happening with high probability. They are never coming out. Yes?
Are the Y's, like the Y1, does it really get fed down to the bottom, actually yellow?
Yeah, this is, again, this is a trick. Typically we do it if you want to really do it by RNN because we know that RNN has a limited memory, so the more we can feed into the model, the better we're going to catch, right? So many people do that, but there is also some drawback of doing that because when you feed it, then you are more restricting your model in terms of the next token. So it's going to lose a bit of innovation. But if you want to really implement a language model using RNN, I would say you definitely need to do that. Questions? Everybody's cool? You got the idea, right? So now, let's talk about the training of this architecture. So if I want to train this architecture, obviously I need to collect a bunch of data. So I'm going to go ahead, collect as much as image I could. And for every single of them, I need to label that by a caption sequence, right? So I'm going to have that. Then I am going to, so for each image, I could have one sample caption. You could have multiple caption for the same image, right? And that image is going to show up as multiple data points inside your data set, right? Image of the cat, the first caption. Image of the same cat, the second caption, and so on, right? Now, once you got this, then you're going to tokenize definitely your words. So everything that you have inside your caption, you should be able to represent it by a sequence, right? So it means that you tokenize, you just find like subwords or words, and then you write them into a dictionary, you label them with different indices. Now you can represent every caption by a sequence of tokens, right? Once you have done, then you have your data ready. Then you're going to pass every single image through the CNN. You're going to get the features, right? Once you got the features, you're going to pass that features forward in time, right? It is going to come and give you some outputs, right? Initially, those outputs are totally irrelevant, right? They are just random tokens, right? Meaning nothing, because you have not trained yet, right? So you pass it through RNN. With a start, every time you could even feed this next token into your neural network, and then you generate the next tokens, right? Once you're finished with the sentence completely, you got into EOS, then you have finished your forward pass, right? Now you're going to end up with a bunch of values. If you want to think again in terms of details, well, here inside CNN you have a lot of convolutions and activations, right? You have all of them, right? This is what happens inside your CNN. Probably you have done a bunch of pullings, right? You have also the output of the pullings in your forward pass. Then you get here, you're going to get a bunch of hidden states, right? And inputs, right? And a bunch of outputs at every single time. Now, these are the things that you have. What you're going to do, you're going to go ahead and compute the loss, right? You look at the output of your language model or your RNN, right? And it's just telling you blah, 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 right? Something totally irrelevant, right? Potato, carrot, lovely, right? Something like this. It's totally meaningless sentence, right? Then you're going to compute the loss between that one and your caption, right? Make sense? You're going to compare it to the true caption that you have, right? I wanted the first one to be it says it, right? Now, I am going to compute the probability of it inside the output of my first token, right? And then out of that, I can compute the cross entropy, right? So I'm going to compute the cross entropy between the output and the ground truth sentence, right? And then I move backward, right? I compute the gradient with respect to everybody inside the neuron, my output RNN, right? So with respect to every single hidden state that I have, this is going to help me compute the gradient with respect to all the weights here, right? Now, when I move backward all the way towards the initial state here, right? So I am going to compute all the gradients up to this point, right? And this guy, the features that I'm getting out of the CNN, these are H0, right? The initial hidden state of my neural network, right? I am able to compute the gradient of my loss with respect to that initial state. Make sense? So I am going to be able to get the gradient of the features or a gradient of my loss with respect to the features, right? I have the gradient here. Can I move it still backward? Yes. Is the gradient of the output, right? It's a pulling. I'm going to go backward, right? Backward convolution. It's a convolution. Again, I do a backward convolution, right? So from here, I can compute the gradient with respect to everything inside this CNN, right? All the way back to get to the image input, right? Make sense? Everybody's cool? Now, you have all the gradients. You have the gradient with respect to all the weights inside both encoder and decoder. You're going to update, right? You update if you pass forward the same image. Now, this time it's going to give you a more meaningful sentence, right? This is still, I mean, after one iteration, it does nothing, right? But if you keep doing it for multiple iterations, then at some point it start to give you better sentences, right? The probability of the right tokens after each and being related to the image is going to increase every iteration. And at some point when your model got trained, it's going to give you a meaningful sentence for a given image, right? Make sense? Everybody's cool? So you get the gradient of the features, and of course you are, I think, you backpropagate through CNN to get all the way backward to the input, and you update, right? Make sense? Everybody's cool? Questions? So here again, the guy who is doing the learning for you is the gradient, right? If you have gradient 0 here, the CNN gets disconnected from the decoder. There is no reason for your model to get trained. There's no reason for it to update, side that they are matching each other, right? So the gradient is the guy who is helping you to just move towards making meaningful output. Okay, great. So now, if you want to do inference with this neural network, obviously you can give one new image into that one. If it got trained over enough data, like it has seen so many images and corresponding captions, it's going to get the idea what are the contexts, how it should speak, right? And it's gonna get this CNN to extract the features that you want. Then you're gonna give a start as the first input, right? And then the features from the image come as the hidden state, and you're going to generate the first token, right? You get the first token, you give it to the RNN again, it's going to give you the next token, right? And so on, and it keeps generating up to the point that it just gives you EOS, end of sentence, right? And then you stop, and then you have the whole sentence for the new image, right? Make sense? Questions? Okay, great. So that was the image captioning. So one of the basic encoding-decoding architectures. But there is one more complicated one, which people thought for quite some time about, and that was machine translator. So neural machine translation, people suppose this is a AI complete problem. And what does it mean, AI complete? Like you have heard of NP-hard problem and NP complete, right? So NP-hard problem are the problems which you can essentially, you cannot make a polynomial order algorithm which is possible to solve it, right? So that is what we call an NP-hard, right? Non-polynomial deterministic algorithm, right? Something like this. And then there are a bunch of problems which we call them NP-complete, right? Which you say, if I solve that problem, I essentially solve any other NP-hard problem, right? L0 norm minimization is an NP-complete problem. People used to somehow make a same argument in AI. They say, like, there are a bunch of problems which are AI complete. It means that if I solve them, they need the complete or human level understanding. And if we can solve that, or if we can design a machine which can solve that, we can essentially solve any other AI problem. Well, it turned out this is not really the case because we have the translators now. I mean, we had them for a long time. They all worked fine at some point after 2015, and we had been never to the human level understanding. We are still not there, right? So this is not really AI complete, but for quite some time people thought this is AI complete, okay? So what is the idea there? You have a sentence, you get the sentence in one language, and then you want to just get the right translation. And by right translation, what do I mean? I mean, you obviously know that you cannot translate word by word, right? Most of the time it doesn't work, right? The words are getting somehow permuted inside the target language. This is one thing. And sometimes you say something in one language and you totally express it in different way in another language, right? They're both saying the same thing, right? And if you ask a native guy, how do you translate this? They are giving you totally different notion, right? Different words, right? But they're talking about the same thing. This was why people thought this is very complicated, because I need to extract information from the source sentence, right? And then I try to give it into one machine which is able to talk fluently in the target language, and it gets the idea, right? And it starts to talk in that. But you can guess this is again an encoding-decoding problem, right? If I have an encoder which can process the source sentence properly and extract the notion that it's talking about, then I can give it to a decoder, and the decoder can start talking about that notion in the target language, right? So let's consider one example. So we want to build one model which is capable of translating from German to English, right? So this is a many-to-many problem, right? So you have a sequence, you want to generate a sequence, right? We need to have a sequence-to-sequence model. We have one sequence in the German language. This is the source sequence, the input, right? And the label or the target sequence output is the sequence in the English language. And they are generally different in length, right? You can say something very short in German and then you need longer sentence in English and vice versa, right? Make sense? Okay, so that is the problem. For encoding and decoding, what do you suggest to be the encoder? What do you suggest to be decoder? Both of them are RNN, and based on what we know up to this point, right? We're shortly going to learn we can use transformer as well, but up to this point, you probably would tell me RNN, right? Because I want to process one sequence, so the input is a sequence, RNN should be a good choice for processing that input sequence, right? And I want, again, a sequence model and the output which is capable of generating a sequence, so probably, again, RNN is a good choice, right? So I can use a basic recurrent network or maybe LSTM or maybe a more advanced one if you want to build some new RNN from scratch. And I can use that to generate my translation, right? Okay, cool. Now, let's first of all think about how would this model work. So if I want to translate, probably I get this input, right? So the input is the German sequence, right? The German sentence. And then I start with one initial hidden state. I can choose it randomly as I wish, right? It's not a very important thing, right? Because I want to just encode it, right? I want to extract the information inside the German sentence, right? So I'm going to give the first token inside the German sentence. I get this hidden state, right? That hidden state goes with the second token. It's going to give me the next hidden state. And so on, right? Once I am over with the whole German sentence, this very last hidden state, what does it contain? It contains information about the whole sequence, right? The whole German sentence. So if everything works perfect, it is going to represent what is really this German sentence about, right? But it's, again, showing it with a bunch of features which are just numbers to me, right? But they are understandable for the neural network itself, right? So it's going to give it one representation, numerical representation of what is this whole sentence about, right? And then you're going to give this sentence into the second RNN, right? Now this guy should be the hidden state of the initial hidden state of your decoder, right? So this is what you got out of the German sentence. You're going to set it as S0. S is now the hidden state of your decoder, right? S0 goes inside, then you can put here as the initial input start, right? Start the sentence. And it's going to give you the first token in English, right? It's going to give you the first English token. You're going to get that English token. You put it here, right? Make sense? The first English token goes in. You have S1. What is S1 about now? It's talking about S0, which is the last hidden state of your encoder, right? Is everything inside the German sentence, right? And then S1 is telling you whatever was inside German sentence plus what you have already talked about, right? And then you can generate the second token, right? And you come here again, whatever you had in the German sentence and the first two tokens, right? And you keep on going till you finish, right? Here at the very end, you get end of sentence, right? It stops. Make sense? Yes?
Here, the size of your hidden feature kind of dictates how complex of a sentence you can translate, right?
Right, right. But, I mean, when we are using RNN, we're going to talk about that. When you're using RNN, you can, I mean, if you start from very small hidden state dimension, then as you increase, you're going to benefit, right? But at some point, you're not going to benefit anymore because the memory is so limited that larger hidden state is not useful. But your intuition is totally right. The size of that hidden state is somehow explaining how capable your model is in extracting context, right? Questions? Everybody's cool? Makes sense? How does this work? Okay. Great. Now, if we want to think in terms of data set, how we can collect data set, well, you need to go ahead, get as much as German sentences as you could. You need to get reliable translations as well, right? Someone native is translating it into English, right? Then you get those German sentences, their corresponding translations, right? Again, for one sentence, you might have multiple translations, right? You could collect all of them, all of the native or all of the globally accepted translations, right? And you can put all of them inside your data set, right? Every time, the guy that is, then you need to tokenize, right? And obviously, when you tokenize, you need to take care of both German words and English words, right? Because your dictionary should be able to take German words and English words, right? Make sense? Yeah, so once you tokenize it, well, then you can keep giving some tokens inside, right? And then you're going to get the hidden state. Obviously, we are not using the output at the encoding, right? Because we're just trying to encode. We're just trying to extract the context, right? Now, this is not a good idea. You can guess. Because there are a bunch of outputs why we are not using it. This is actually what motivated people to do attention, and then attention ended up with transformers, right? So we're going to talk about that, but right now, we're not using the output in the encoding, right? Now, when you are doing the decoding, obviously, again, this guy goes in. Every single guy that comes out here from your neural network is softmax output, right? So Y1, for instance, is a softmax output. And then this softmax output is telling you what is the chance of every single token happening, right? Make sense? And then you hope that the token happens, or the token, which is the right token for translation, has the highest probability, right? Make sense? Yeah. Now, one thing that you can do, obviously, here is that when you are sampling at the output, since you know that your samples should be only English tokens, right? So you can manually mask out the German tokens, right? You would say, I don't want to select from German tokens because I want to translate to English, right? And then you can just compute the softmax on the English tokens, right? So it's going to give you the probability of the English tokens. It's just a manual thing. But if your model is extremely complex, if everything works fine, even if you don't do that, it should eventually at some point learn to just give you English tokens, right? Questions? Everybody's cool? Okay, so that is what you are going to get. Now, if you want to do the train, obviously in your data set, you have the target English sentence, right? So that is what I'm showing by V1, V2 to VL, right? These are the tokens, the English tokens that you want your neural network to give out, and you use it when you are doing the training, right? So you basically compute the loss between your output and those tokens, and obviously you're going to use cross entropy, right? Make sense? Okay, great. So if you want to do the training, we are going to start with nothing. We give the German sentence. At the end of it, it's EOS, end of sentence, right? Now you have the hidden stage, right? Once you see EOS, you know that the encoding is over, right? And then you're going to get that encoding. You give it here, right? You start with the start. That goes out. You give the next token that you have predicted. You get the next token, and so on towards the very end. And then you compute the cross entropy here, right? Once you computed the cross entropy, obviously you can go ahead and compute the gradient with respect to all the weights inside your decoder, right? Make sense? So you're going to compute, so you move backward, and when you move backward, you compute the gradient with respect to all the weights inside the decoder. You also get the gradient with respect to your initial stage, right? Right? When you are doing back propagation through time, right? And that gradient is the same gradient as the gradient with respect to the last hidden state of your encoder, right? Which means that if you look at back on your encoder, you have the gradient at the output, right? Again, you can move all the way backward to compute all the gradients with respect to hidden state in between, right? And they are going to help you to compute the gradient with respect to all weights inside the encoder, right? You have the gradient at the encoder and decoder, you update all of them together, right? You repeat, you keep on repeating, right? And hopefully at some point your model starts to learn to map the right German sentence into the right English sentence. Make sense? Questions? Do you find all of those back propagation that we talked before useful now? Helping you understand how the learning is happening inside these architectures, right? So this is the point where for many people these guys are black box, right? AI is a black box. It's not, right? You do see it, right? It's a gradient moving, right? And when the gradient moves, it's going to update. Because the gradient is pushing you towards the minimum loss, then you're going to get your neural network to somehow pass any German sentence to the right English sentence based on what it has seen, right? If the language has a limited entropy, limited confusion, other sentences are going to be close to whatever it has seen before, right? And then it can guess what is the right output, right? It's a kind of interpolation that it does. Make sense? Questions? Great. So that's the way that you do the training. Now let's consider one example and see, for example, somewhere in between the training, what could happen with that example. So anyone knows what is this sentence? Anyone speaks German? Das gefällt mir? Anyone? No? So do you know what does it mean literally? Das gefällt mir? It means that mir in German is like to me. Das, that feels to me, right? This is the way that a German person would say, I like it, right? It's like, I like this, so it means that it feels to me, right? This is the way that it says it, but you don't say it like that in English, right? Now, if you wanted to translate it word by word, it would be that feels to me, right? But it's a wrong translation, obviously, in English. Nobody says like that in English. In English, you would say, I like it, right? So it is one sample inside your data set, right? Okay. Now, what's going to happen when you do the encoding? You start with the initial state. You say the sentence is started, right? Then you're going to get one hidden state, right? The sentence started. Now, you're going to give the first token. Say that token is representing das, okay? Then you're going to get that token plus the memory, and you're going to update the memory. This H2 is telling you that it's a German sentence with the first word being das, right? Gefällt goes in, this memory goes in, and then it's going to generate the next memory, right? That is going to tell you that is a German sentence. It started with das, then there was gefällt, right? And then after that, the last token goes in, and you're going to get this memory, so it's going to capture all the information inside that sentence, right? But that is just a representation. It's not telling you literally that the sentence is das gefällt mir. It's just somehow memorizing. It's a sentence, it's talking about something, and someone who is the first person singular is liking it, right? So it's a kind of that concept being encoded into this hidden state, right? Once it sees the end of sentence, then this is the last token, right? So it's a short sentence talking about that, right? And now you have this encoded, you give it to your decoder, right? What does the decoder do? It's going to look at that when it says, okay, I need to speak in English. It's the start of the sentence. And I want to talk about single person singular, right? First person singular, right? So I should start probably with I. This is the way that I say in English, right? And I want to talk about something being very nice, or I feel very good about that, right? So the right way of saying it is to start with I, right? I'm going to start with I, and then I'm going to give I as the first token. Then again, the RNN would tell itself, okay, I already have said I, right? And I want to explain that I find something nice, right? So it means that the next word is probably like, right? So I'm going to say I like, Make sense? Now, the next time you're going to give this hidden stage, right? And this hidden stage S2 is capturing the information inside the German sentence, so you still know what you're talking about, right? And also it's telling you that you already have said I like, right? Well, there is no other word that you can put here, right? The right word should be it, right? I like it, because the sentence is supposed to explain that something felt nice to me, right? And I started to say I like, so the last token should be it, right? End of sentence, it's over, right? Make sense? Questions? Great. So, here, one thing that could happen inside this language model is that when it's generating things, right, it relies here, when it wants to say like, it relies on I, right? It relies on the fact that it's talking about that German sentence, right, plus the fact that it has said already I, right? But that thing is not going to happen all the time, right? Because you do know there are lots of randomness going on inside this neural network, right? And then if a random seed changes, if the sampling that you are doing changes a bit, right, the output could change slightly. What do I mean? Let's say that it wants to start the sentence, right? And when it starts the sentence, I'm sorry, I give you a short break soon, sorry. So let's say that the language model wants to start, right? Start of the sentence, and it wants to take the sample of the first token, right? How can it take that sample? Well, it could look at the probability that it sees at the output of the softmax and take the token that has the highest probability, right? It's one way to do it, right? This is probably the way that you think of, right? Make sense? But you do know that when you want to start a translation, you do not need to necessarily say always the same sentence, right? You can translate one thing in multiple ways, right? And all of them are probably likely output for you, right? So you could, for example, take a random token based on that distribution. Does it make sense to you? So on Python, you write down categorical distribution, you give the softmax output to it, it's going to give you one token, right? And that token is one of the likely tokens your softmax has computed, right? Make sense? Okay, so this is what I mean by sampling, but let's for the moment, because you are used to, assume that your output, your softmax, whatever it gives you, you're going to sample the guy which has the highest probability, right? At the end of the day, all of these probabilities are computed numerically, right? They depend on the token that you, seed that you started. It depends on the initialization that you have done inside your encoder and decoder. So let's say that when you compute it, it could give you the token it with this probability and token I with this probability, right? They are very close, but it is a tiny, tiny bit more than I, right? So it's going to happen that it's going to sample it, right? Make sense? You see that? Okay, so you're going to sample it. Once it samples it instead of I, then it goes in, right? What does the neural network say? It says that, okay, I'm talking about this sentence, right? I already have said it, right? So I cannot say like anymore. It doesn't make sense, right? It's not a right English sentence, right? Given that I already have said it, then I should say fills, right? It was not a good choice, but anyways, I have already said it, right? What is gone, right? So it fills, right? Then for the next token, what does it say? It says, okay, it fills. I cannot say it again, right? I need to complete this sentence, right? To me, end of sentence, right? Make sense to you? Everybody's following? So this is what could happen to you, right? When you train a neural network with limited data, unlimited capacity, right? Because at the end of the day, you do not get the perfect output, right? Nothing is going to work perfectly, and then things could just go a bit south. Yes?
Is it fair to say that overfitting is good in the translation case? Because when we learn languages, we try to memorize the standard phrases.
it could be, right? But the point is that for translation, you mean that you do over... well, it has its own drawbacks as well. So I'm not expert in language model or translation in particular, but what I could imagine right now is that because many sentences are sarcastic, right? And then in different situations, they just transfer different meanings, right? If you want to be so obsessed with those context, then your neural network start to get confused. Because you can see a bunch of phrases which are referring to the same thing, and it somehow concludes that always when I see that, I should talk like this. Whereas when you just use a sarcastic argument, then it just simply does a mistake, right? So I could not say it for sure, right? But obviously, if you keep training more and more, this behavior is going to happen less and less, right? But as I said, at the end of the day, you are not going to take the guy with the highest probability. You always sample because you want your neural network to look like a human being, right? It just talks a bit randomly, right? It doesn't always say the same thing. Make sense? Questions? No question? Okay, so I'm going to just finish this tiny part and then I give you a short break. Now, the better idea here would be that when I am doing the translation, right, I do not immediately translate this guy to be I, right? I would say it could be I, it could be it, right? Let's see what's going to happen next, right? And then I sample the next guy, right? And again, I would say for the next guy, I have like as one likely option. The second one is feels, right? Now, let me match I and it with those next tokens, right? I like has high probability, right? I feels has very small probability. It cannot happen, right? It like never happens. Probability present by 0. It feels, it again has a high probability, right? But it feels probably has lower probability than I like, right? And I can keep on going, right? I get the next token, I like it. It has a probability, right? It feels to me. It is again likely to happen. But the likelihood of this second one is much smaller than the first one, right? So I couldn't say at the very first token, but now I can say it, right? When I keep going. So it's a better way to do the sequence decoding, right? In these architectures. Everybody sees that? So it means that I just take the whole complete sequence at the output, right? And then I think about the sequence which overally has the highest likelihood. Make sense? Questions?
How do you do it? You generate multiple sequences?
Yeah, we're going to talk about it. I mean, this problem you cannot solve it. It's NP hard. It's exponentially hard. You know? Everybody's clear? Okay. Now, can you tell me what is the complexity of this search? Because I need to compute lots of probabilities, and then I need to search among all of them, right? Let's think about one simple example. Say my sentence is of length 3, okay? And in every single of them, I could have 10 different tokens. Well, you know that 10 is very small, right? 100,000 is a normal one. I told you last time, right? How many tokens you have in English, right? But let's say we have only 10 tokens, right, in this dummy example. I have 3 different tokens in my sentence, right? How many possible cases do I have? 1,000, right? Why? Because you would say the first place could get any of the 10 tokens, right? The second place could again get any of 10 tokens, right? The third one could get again any of 10 tokens, right? 10 times 10 times 10 is going to be 1,000, right? Now, if you think about size L, right, length L, and every single guy has d different tokens inside the dictionary, right? They're going to be d to power L, right? Impossible, right? 100,000 to power, I don't know, 20, right? A sentence with only 20 tokens. It's impossible for you, right? You can never do that. Make sense? So this search sounds very promising. It's going to make your translation significantly better. but this is computationally very complex, right? So the idea that I said is to just wait forever for the whole sentence to be over, then you consider all possible combinations, and then you take the combination, the final sentence, which has the highest probability, right? Make sense? So, but this one is a quite complicated thing to compute in practice. Now, if you just want to think how you can compute the probability of one sentence coming out of your decoder, again, you can think in terms of the conditional probability. You could say, what is the probability of the whole sentence 1 to L coming out of my decoder when I have given this? So this X is the German sentence, right? Das gefällt mir comes here, and then you are just computing the probability of every single possible translation, right? Make sense? Now, I can write it down in this form. First of all, X, the whole X is represented by H, right? This is what I extracted by my encoder, right? So I'm going to replace it here. Now, I want to just open up this term. Have you heard of Bayes' rule? Yeah? Have you heard of it? So how do you open it? I write it down V1 given H, right? Times V2 given H and V1, right? Times V3 given H and V1, V2, right? And so on, right? So this is the Bayes chain rule. If you do that, then you're going to get product of these terms, right? Make sense? Now, if you are at one particular time in the decoder, this HT and all of V before, all of the decoded versions before, where do you find them conceptually? What is the guy representing all of them? Not the output. Output is giving you the probability of the next token, right? Which guy in your decoder is capturing whatever you had in the encoding in the German sentence plus whatever you have set up to now? The state, right? The hidden state of your decoder, right? So this means that I can drop this guy, right? I can drop this guy, and I can simply write down the hidden state, right? Make sense? Make sense? Okay, so you have this one. You can also take the output of the previous time if you are really feeding it into your decoder, right? So every time you get a word, you just feed it in, right? But if you don't do that, you can drop this red one, right? Now, if you do that, then now this guy, do you know how you can find this guy, where you can find this guy? What is the probability of the next token given whatever you had up to this point? How do you find this? The output at that time, right? If you think about why, the output of the softmax at that time is giving you all the probabilities, right? So that guy is the one which you need here, right? So what does it mean? It means that I look at the probability of all tokens at my first time, second time, and so on, and consider all possible combination of them, right? First token, first token, first token. Oh. Okay, I'm going to, yeah. I am going to just get I'm going to get all of those probabilities, right? And then multiply them. And then I want to think about other sentences, right? First place is the first token, second place is the fifth token, third place is the fourth token, and so on, right? I multiply their corresponding output, right? And this is going to give me the probability. Make sense? So this is the way that you can compute that probability. So I have given here one example. As you can see, like if I am thinking about one token, which is the second token in my dictionary, right? If the output of my decoder at one time is this guy, then that probability is going to be 0.3, right? Make sense? Okay. So if you do that, then essentially what you need to do, you want to maximize this guy. So in other words, you want to maximize this term, right? I am just taking the logarithm because logarithm does not impact on optimization, right? And then this makes the product into summation, so I'm going to have this one. But the key point here is that the number of cases that you need to search among is essentially exponentially large in terms of the number of length of your sequence, right? Which is not a practical thing. So what you can do in practice, you are going to use some tricks. And those tricks are usually just to limit your search among the, say, viable choices. So one thing that you could say among all of these exponentially large cases that I'm considering, one of them is a totally redundant sentence, right? So IR potato is also a possible sequence at the output, right? The first token is I, the second token is R, the last token is potato, right? But it's not an English sentence, right? It doesn't have the right syntax, it doesn't have meaning, right? So there are lots of choices like this there, right? Which you do not really need to care about. And they have extremely low probability to happen, right? So you can simply ignore them. And if you think like this, then you probably can limit your search among a smaller space. And one of the very simple ideas that people do is the beam search. If you want to implement this architecture by an LSTM with a very simple implementation, and at the same time it works fairly fine, you can use this idea of beam search. What is the idea? It would say, okay, I'm going to keep one top K choice, right? K is one number, right? Let's say I just keep K to be 5, right? So every single time I am going to take the sequence up to that point, or the 5 sequence up to that point, which have the highest probability. In the first token, I'm going to keep the 5, in the first time, I'm going to keep the 5 tokens, which have the highest probability, right? Then I go for the second time. Now, I had the 5 highest probability tokens from before. I am going to just match them with every single new token, right? And then among all of these cases, again, I select 5 sequences of length 2, which have the highest probability, right? Every time that I progress in time, I just keep the 5 highest, the top 5 sequences, right? And when I am over with the sentence, I select the one which is highest in probability, right? Make sense? So this is what we call it beam search or top K search. And that used to be a kind of conventional way of implementing the decoder, especially when you are doing language tasks like translation, right? Because this is the feasible one. You don't get into the exponential complexity. Questions? So you essentially are going to approximate this guy always at every single time with the 5 highest one, right? And this hopefully, it's not necessary, I mean, it's obvious that there could be some cases in between getting lost, right? But at least it doesn't get you into the example that I told you, right? So you don't get super sensitive to a tiny mistake in one of the tokens. Questions?